what we aim to do from the very beginning of this matrices section, if you remember, I'm going to quickly share this picture with you. Share and share that one. All right. All right. So remember, this was the very first one, and I said, what happens if you need to solve something that looks like this? Well, system of equations, you can find the values quite easily because that's a very easy system of equations to solve. But when you get to something bigger, it gets far more complicated very, very quickly. So we've done everything up to the end, and we got to a state where we came to this. All right. And I am going to be working on that now. All right, so I'm going to whiteboard. All right. So let us even keep color consistent. Let's work in purple. So we currently are sitting in the situation where we have 1, 1, 1, minus 1. And then we have x, y, and 3, 1. Now we need to try and find a way that we're able to get rid of this bracket over here and end up with just this essentially vector, because a vector is just a single column or single row matrix, equaling another vector over here. And then you'll just be able to read x equals blah, y equals blah. Now, so Tyler, will this come up in core and extended? That's a great question. I'm not 100% sure, but I will check for you. I think the simple stuff, the addition, subtraction will come up in core. I don't think what I'm going to be doing now will come up in core. But as I said, I will check for you. Yeah, as I thought. So in extended, it's definitely there, but I don't think it's in core. All right. So the big thing is we want to try and essentially divide this to the other side. So you've got a matrix multiplied by another matrix equals that. So we want to divide. And the problem is besides the fact that you'll be sniveling into your mouth and weeping incredibly terrible tears, there is no division available in matrices. Now you go, what? How is that even possible? You can always add, subtract, multiply, divide. I mean, it's one of the basic operations. Well, that's stuff that you know about numbers. Matrices are different entities entirely. As we've seen, how you add, how you subtract, even how you multiply, very different. But luckily, division has another side of the coin. Remember, if you have something like 2x equals 1, and I need to divide the 2, I can essentially, instead of dividing the 2, I can times by a half. And I still get the same answer as a half. And you're like, of course you can do that, because dividing by 2 is the same as times by a half. We know this. Well, let's just slow that sentence down a little bit. Dividing by 2 is the same as timesing by something else. We know how to multiply matrices. So we need to try and find a way of changing this divide into a multiplication. Multiplication we can do. And this is where we come to the inverse of a matrix. The inverse is what you need to multiply in order to divide, or essentially have the same effect as dividing. How do you calculate a matrix? How do you calculate the inverse of a matrix? So I'm going to deal with a 2x2 matrix only because I'm pretty sure that's the only one you're going to have to worry about. When you get to varsity, you'll come up to 3x3s because it's very much more complicated. 2x2s, nice and simple way of doing it, and then we can multiply. The inverse is denoted by a -1 exponent. That's very interesting. All right. So you use almost like an exponent of -1 to symbolize the inverse. And what you do, you need to listen very carefully to this. You swap the values on the diagonal. I'm going to change color here. Try and make it something that stands out. On the diagonal, you swap. So it becomes D over there, and it becomes A over there. And then, on your other diagonal, you just make them minus. But they don't swap, they stay. So it becomes -B and -C. Oh, close the bracket in the wrong color. Now, that's 2 steps out of the 3 steps we need to do. So I will make a note here. There are 3 steps. Number 1 is my green diagonal. So green diagonal swap. Number 2, my blue off diagonal. I'll call it the other diagonal. We make negative. And then number 3, we need to work with the determinant of our matrix. What is a determinant, you might ask? I'm very glad you're asking. So we need to divide by 1 over the determinant of this matrix. That's nice. I still haven't answered your question. What is a determinant? So determinant is essentially a scaling factor, and it is multiplied, it is calculated in the following way. So the determinant of this matrix, let me get some better brackets there, just so that I don't confuse you. Draw. So the determinant of this, you multiply the diagonal, A times D, you always subtract, and then you multiply the other off diagonal. So you multiply down minus multiply down. So it kind of forms like a cross. So it forms like a cross shape. So you always do that for a determinant. So let us now actually have a look at our problem. Getting rid of all of these. I'll leave those steps on the side, and then I can get rid of all of this. Okay, great. So my matrix is this one here. So if I want to calculate my inverse of this matrix, I said I needed to swap my diagonal. So green. So I get -1 and 1. This is true. It is true. The first part of solving any problem is noticing that there is one. 100% correct. And then we need to make the other off diagonal negative, but staying in the same place. So 1 becomes -1, and then -1 becomes 1. There is a reason that you swap and don't swap and make negative. To be honest, you don't need to know about it. That only becomes more crucial when you start doing bigger matrices. So I'm going to leave that for now. And then we've got to have our 1 over our determinant. All right. And how do we calculate my determinant? So the determinant of 1, 1, -1, oh, that's not meant to be a -1. Silly, silly me. All right, so when you make minus, that's meant to be a -1 as well. So let's just correct this. Great. Can take that off and draw in purple. All right, so we multiply here. So it's 1 times -1 minus, and then this one is 1 times 1. So 1 times -1 is -1, -1 gives me -2. Let me just make that a little bit neater as well. All right, so it's -1/2 into this bracket. Now, one thing I haven't covered yet is what happens about this number in front? All we've dealt with is a matrix times a matrix. This is a little scalar in the front that, when multiplied in, actually multiplies, understandably, to everything in the matrix. So when I multiply this in, I'm literally multiplying it to that one, to that one, to that one, and to that one, because it itself applies to the whole matrix. So this leaves me with a matrix of 1/2, 1/2, 1/2, and -1/2. If you want to write as a fraction or a decimal, doesn't matter, that's totally up to you. So here we have found our inverse, which is great. Is that our solution? No. Because what is our actual problem? So our problem is us trying to find the answer of x and y from our system of equations. All right. So if I multiply this on the front, and then x, y, notice I've put this matrix first. That means I need to put the matrix first over here as well. If you look up in textbooks, you'll notice that the order of multiplying matrices is very important. And you're like, yes, I remember you saying this. Richard, I remember you saying that the order matters because you need to make sure that the dimensions on the inside are equal so that we can multiply, and then the answer will be the dimensions on the outside. I'm so glad you all remembered this. All right, so that is why as well we need to pre-multiply, being at the beginning, and not post-multiply at the end. Now, the amazing part about all of this is if you multiply a matrix with its inverse, you end up with the identity matrix, which is fantastic. But maybe you don't believe me. So let us quickly check that it actually works. So the answer from this multiplication, this is a 2 by 2, this is a 2 by 2. The middle dimensions are equal, which is great, meaning that the answer is going to be a 2 by 2 because it's at the outside. So we multiply. Remember when we multiply, you multiply row on the left, column on the right. So a half times 1 plus a half times 1. Then on this side, you have a half times 1 plus a half times minus 1. On this side, it is a half times 1 plus minus a half times 1. And over here, it is a half times 1 plus minus a half times minus 1. All right, so let's simplify. A half plus a half, great stuff. That gives me 1. A half minus a half gives me 0. It gives me 0. This one over here, a half minus a half also gives me 0. And this one is a half minus times a minus makes a plus. So a half plus a half gives me 1 as well. All right. So we can see that when we multiply the matrix with the inverse, we do indeed get the identity matrix. We get 1. And that totally makes sense because if you take 2 times a half, you get 1. So this is the idea of what we're doing, except remember 1 in matrix term is an identity. All right. And this, if you multiply by xy, will just give you my bracket xy. Why? Because anything multiplied by the identity is itself. Anything times 1 is itself. Great. Now we've got to multiply this. Can we do it? Let's check dimensions. 2 by 2. This is a 2 by 1. So these two inner dimensions are equal. Therefore, the answer is going to be a 2 by 1. That's a good sign because I want it to be a 2 by 1 since this is a 2 by 1. And then I'll just be able to read across. So let's multiply. So we have a half times 3 because it's row times column. So it is a half times 3 plus a half times 1. And then we have a half. Actually, what I'm going to do is I'm going to move this up slightly. So that I can keep alignment going. That's very handy. All right. So it's a half times 3. Great. And then we have a half times 3 plus minus a half times 1. So when we simplify this, a half times 3 is 1.5 plus a half gives me an answer of 2. And then we have a half times 3 is 1.5. 1.5 minus a half gives me an answer of 1. And now, if we happen to go back to our original lesson, we will see that we solved this already. I'm going to save this. I'm going to in that. I'm going to totally lose this. There we go. Right, I'm going to share this. And we see that we came up with the answers of 2 and 1, which means that we have actually just solved that system of equations. So as amazing as that is, you might be thinking to yourself, that's nice. That is a hell of a long way of doing this. I can do simultaneous equations far quicker than I can write it as a matrix, eliminate my coefficients when writing it, find my inverse, multiply my inverse with the answer vector over there, and then get my answer. I can do it far quicker simultaneously. Yes. However, the time that it takes to do it on something bigger, like a 3x3, as you see here, or a 4x4, or a 10x10, simultaneous means you're going to be doing this for a year. Whereas with matrices, you can type it into a computer because there are programs out there that you can type in numbers like this and it will calculate something immediately and do it. There are calculators out there, the silver Casios, that can actually do all of this. So that is why matrices are crucial. What we're also going to do in the next lesson, which is the last part of matrices, is using matrices with transformations. So using reflections, rotations, you can do it with stretches and stuff like that. Any enlargements as well. So it's very important that you can see that I used a very basic example, specifically so that you could see you could solve it the one way, but in solving it using matrices, you will get the same answer.